Good afternoon, advanced algebra students. I hope you're having a fantastic day. We are wrapping up the first half of our advanced algebra chapter 1. We did that little introductory lesson, I don't know if you remember, on absolute value, which was from Algebra 1, 5.1. And then we've done sections 1.2 and 1.3. Today we are doing the last section of chapter 1 before we pause, test, and then continue. So this will be the last section for our upcoming test, section 1.3 in our advanced algebra book. Now the topic is on piecewise defined functions. So go ahead and put that at the top of your paper somewhere, section 1.3, piecewise defined functions. We're only going to be doing 3 examples because they take a little bit longer to explain, and I'm just going to pick 3 representative examples, and then we will do more examples, obviously, with our homework. So what I have to say about piecewise defined functions is they have different rules for different parts or different pieces of the domain. So it sounds kind of complicated, piecewise function, but it actually is a very simple concept. It's saying that there are different pieces to the function, and each piece has a different rule. So let's start off with an example. We'll call this example 1. And this is a piecewise function that is defined differently at 3 different places. So we're going to draw the different places. First of all, when x is less than -2, f of x becomes x plus 2. So that's the first piece. Then, when x is between -2 and +2, our function becomes f of x equals -1/2 x. Then, when x is between 2 and 4, our function becomes f of x equals x. Now let's go ahead and see what that might look like. I'm going to put a graph here, and let's go ahead and do just the first part. So the first part is saying when x is less than -2. So we're looking at the line y equals x plus 2. Remember that f of x is just a fancy way of saying y. So if we say that f of x equals x plus 2, we're really saying y equals x plus 2. Now what I like to do is to just graph that whole line and then just erase the parts that we're not showing on the graph. So if I want to graph the line y equals x plus 2, I would start at 2, and then I would either go up 1 over 1, or I would go down 1, back 1. And let me see if I can draw a relatively straight line here. That looks pretty good. Okay, so I've drawn the line here, y equals x plus 2. It has a y-intercept of 2 and a slope of 1. Now notice, however, that because this is a piecewise function, this is only one of the pieces. And this is the piece that applies when x is less than -2. So I'm going to erase the part of the graph that occurs after x is -2. It's also very important to notice that x does not actually equal -2 here. So what I'm going to do is I'm going to put an open circle at -2, and then I'm going to keep the portion of the graph that is occurring when x is less than -2. So now I've graphed the first part of that piecewise function. Now the second part occurs when x is between -2 and +2. Note that it is including -2 and +2. And the line we are graphing is y equals -1/2 x. We might think of that as -1/2 x plus 0. So that means I have a y-intercept of 0, and I'm going down 1 and over 2, or I can think of it as up 1 and back 2. And this is going to be the line that we graph when x is between -2 and +2. So that is the second piece of our piecewise function. The third piece is represented here. And I think I need to correct one of my ends here. This symbol should have just been a less than next to 2, which means I'm going to put an open circle here. It would have been impossible for me to have a less than or equal to on this 2 and a less than or equal to with this 2, because both of these would be including 2 and that would not work. So I knew immediately that this one just had to be less than with an open circle, and now we're going to use the closed circle here. So the third piece is the line y equals x, and that occurs when x is between 2 and 4. So the line y equals x, we can think of that as y equals x plus 0. It also has a y-intercept of 0. And then we go up 1 over 1, up 1 over 1, up 1 over 1, and so on. Now, we are only going to include this function when x is between 2 and 4. So I'm going to erase this part and put a solid dot here, and then I'm going to put a solid dot here and erase that part. So you see we have 3 lines here, or 3 portions of lines, and then we have applied them at various different values of x. Notice there is an arrow on the end of this because this is valid for all x less than -2, but these occur over very specific domains. Okay, so that, I do have some steps written down here, but basically it's just the steps for each of these 3 pieces. If you would like me to review it, step 1 was to sketch the graph when x is less than -2 and use an open dot to reflect that x cannot equal 2. So we did that there. The second thing we did is we sketched the graph for the values between -2 and +2. We used a closed dot on the left and an open dot on the right to match these 2 symbols here. Then the third thing that we did is we sketched the graph between 2 and 4 using closed dots on both of those ends. And if we wanted to determine the range of this function, then we would have to calculate the y values that correspond to the minimum and maximum x values. All right, let's go ahead and do a second example here. So again, we're only going to do 3 total examples. And this will be example number 2. This problem is a little bit different because instead of having a description of a function and graphing it, we're going to be given the graph and then asked to write the description of the function. So let me go ahead and put this here. I'm going to have one point be at -3, 1. And it's going to be a closed circle, and then an open circle here at 0, -1. So that is one piece. Then I'm going to have another piece that goes from here to here. And my third and final piece is going to go from the point 2, 2 with an open circle, and then it's going to go over 1, up 1, and over 2, I should say, like this. So it's also going to go through the point 1, 2, 3, 4, 3 here. I'll add that to the graph. Okay, so if you need to take a minute to pause and graph this, go ahead. What we want to do now is come up with a piecewise function, a description of the piecewise function that would match the graph. So what is the rule that describes the piecewise function shown in the graph? So we write f of x equals, which again is just like saying y equals. And let's determine the different domain range, the different values we have for the domain, or the different pieces of the domain. One piece is from x is -3 to 0. So we're going to say negative 3 is less than or equal to x is less than 0. That's going to be one piece. Another piece is between 0 and 2. So we're going to write 0 is less than or equal to x is less than or equal to 2. And then the third piece is when x is bigger than 2. So we're going to write x is greater than 2. So those are the three pieces for that picture. Now, let's see if we can figure out what the equation of this first line is. Remember, to write an equation of a line, we need the m and the b, the slope and the y-intercept. This line has a y-intercept of negative 1, so my b is negative 1. If I count out the slope, I can see that I'm going down 1, 2, and over 1, 2, 3. So the slope is negative 2/3. So this is the line y equals negative 2/3 x minus 1. So I already have the y equals portion of it here, and I'm just going to write negative 2/3 x minus 1 there. So that is the function defined when x is between negative 3 and 0. Now, the next piece is this piece right here. That is simply the line y equals 1. So this is our y equals, and we just write 1 there. This line right here, this horizontal or line segment, is where y is always 1. Now let's see if we can figure out what is the equation of the line when x is bigger than 2. I can see if I go back here, if I go, instead of up 1 over 2, if I go down 1 and back 2, I can see that this line would hit the y-axis at 1. So this line right here has a y-intercept or b of 1. The slope, if I count it out, is up 1 over 2, so it's 1/2. So this is the line y equals 1/2 x plus 1. So I'm going to write the 1/2 x plus 1 here. And that would be it. That is a piecewise function that describes the graph that we were given. So I hope that was helpful. Okay, we have one more example. Again, we're only doing 3 examples because these do take a little longer to discuss. And we will do more examples, obviously, during class when we do our Zoom. So this is example number 3 with piecewise functions. So this question says, and this is similar to some of your homework questions, how can you write the function f of x equals the absolute value of 2x plus 1 as a piecewise defined function? So I'm going to give you the steps. The first step is to write the function in the form f of x equals a times the quantity in absolute value marks, x minus h plus k, so that we can find the vertex. So if we have our original function here, what we can do, if we would like, is write our original function as y equals the absolute value of 2 times x plus 1/2. So what I did is I took a 2 out of this expression here. These two expressions are equivalent. If I distributed the 2 here, 2 times x would be 2x, and 2 times 1/2 would be 1. So I'm not changing the value of the function, I'm just reformatting it. Now the absolute value of 2 is 2, so I can take that out and write this as 2 times the absolute value of x plus 1/2. And if I want to, I can also say plus 0. Now that I've kind of reformatted this, I have not changed the value of it, it is easier for me to see what the vertex is. Remember that when something is an absolute value function in this format, h and k are our vertex. So the vertex of this function is what? See if you can figure out what the vertex of that absolute value function would be. The vertex is -1/2, 0. Remember, there is a minus sign built into the absolute value formula. So this is like saying x minus -1/2. All right, so we've got the vertex at -1/2, 0. Let's go ahead and graph that. And put a dot right here at -1/2, 0. Now, the graph has two pieces. One piece is going to be to the left of the vertex, and the other piece is going to be to the right of the vertex. So we want to write equations for the line segments to the left and to the right. So let's figure out what that line segment would be if we were going to the left. In this particular case, we know if we were going to graph this, that our slope on the right-hand side is 2. So let's go ahead and actually graph all of the absolute value function. That might make it a little bit easier, and then we'll figure out the two line pieces. So when we're graphing an absolute value function, we graph the vertex, which is -1/2, 0. Then because A is 2, that tells me that the right-hand side of my graph has a slope of up 2 over 1. So I'm going to go up 2 over 1 and put a dot here. Likewise, the other half is going to be symmetrical to that. So I'm going to go up 2 and back 1 and get the other half. Now, let's go ahead and figure out what these 2 points are. This point is the point 1/2, 2. This point is the point -1.5, 2. And this point, as we already know, is -1/2, 0. We're still trying to come up with the equations of both sides or both pieces of the graph. So the first line, again, to write an equation of a line, we need an M and a B. The first line has a slope of -2 because we're going down 2 and over 1. If we want to find what B is, we can plug in the slope as well as the point that we've been given. Here's our X and here's our Y, and solve for B. So I have 2 equals -2 times -1.5 plus B, or 2 equals +3 plus B, or B equals -1. So what this tells me is that on the left-hand side of the graph, my line segment has a slope of -2 and a y-intercept of -1. So we're going to say that f of x is equal to, when x is less than -1/2, the line will be y equals -2x minus 1. That's a lot of work just to get to that point. Now we're going to do the same thing for the right. So this is going to be the second line. The second line goes to the point 1/2, 2, and has a slope of +2. So my M is 2. Again, I want to plug everything in to y equals mx plus b. This time I'm plugging in this point. So I'm going to write 2 equals 2 times 1/2 plus b, or 2 equals 1 plus b, or b equals 1. So my second line has a slope of 2 and a y-intercept of 1. So f of x would be equal to 2x plus 1 when x is greater than or equal to -1/2. Notice that one of these symbols does not include -1/2 and the other does. We could not have a less than or equal to here and a greater than or equal to there because we would be including the same point twice. So we are just including the negative 1/2 here, but not there. All right, the question that I had originally asked on my notes was, can every transformation of the absolute value function be written as a piecewise defined function? Yes, because with absolute value functions, there are two branches. One where the graph is decreasing and one where it is increasing. So we can write any absolute value function as a piecewise function with two pieces. All right, I know this was kind of tough, but I'm looking forward to helping you in class. Thanks for listening. Bye.